Terraforming Mars, turning a barren planet into a second Earth. Introduction. Mars has long captured the imagination of scientists and visionaries as a potential second home for humanity. However, the red planet presents extreme environmental challenges, including a thin atmosphere, sub-zero temperatures, and an absence of liquid water. Despite these obstacles, advancements in planetary science, engineering, and biotechnology have fueled serious discussions on terraforming Mars, the process of altering its environment to make it more Earth-like and habitable. While still theoretical, terraforming remains one of the most ambitious concepts in space exploration. Could we transform Mars into a planet capable of sustaining life? What technologies and methods might make this possible, and what challenges stand in our way? Why terraform Mars? Terraforming Mars is not just a bold dream, it may be a necessity for humanity's long-term survival. The key motivations include ensuring the survival of humanity. 1. Establishing a self-sustaining colony on Mars would provide a backup for humanity in the event of a global catastrophe on Earth. 2. Expanding human civilization beyond Earth ensures resilience against threats such as climate change, pandemics, or asteroid impacts. Scientific and technological advancements. 1. Mars offers a unique natural laboratory for studying planetary evolution, climate dynamics, and potential extraterrestrial life. 2. The development of terraforming technologies could lead to breakthroughs in biotechnology, atmospheric engineering, and space resource utilization. Long-term economic and industrial potential. 1. A terraformed Mars could enable large-scale mining, manufacturing, and energy production, paving the way for interplanetary trade. 2. Technologies developed for Mars could be applied to climate engineering and sustainability efforts on Earth. Major challenges of terraforming Mars. Turning Mars into a habitable world presents significant scientific and logistical challenges, including lack of a dense atmosphere. 1. Mars' atmosphere is 99% thinner than Earth's, composed mostly of carbon dioxide. 2. Without an atmospheric buffer, Mars cannot retain heat, making it too cold for liquid water. Absence of a magnetic field. 1. Unlike Earth, Mars lacks a planetary magnetic field, which exposes it to intense solar radiation and atmospheric erosion. 2. Any newly created atmosphere would be vulnerable to being stripped away by solar winds. Extreme cold and dry conditions. 1. The average surface temperature is -63 degrees Celsius, -81 degrees Fahrenheit, with nighttime lows reaching -125 degrees Celsius, -193 degrees Fahrenheit. 2. Most of Mars' water exists as frozen ice beneath the surface or in polar ice caps. Resource limitations. 1. Essential elements such as oxygen, nitrogen, and liquid water are scarce on Mars. 2. Long-term sustainability would require extensive resource extraction, or off-world supply chains. Proposed methods for terraforming Mars. Scientists have proposed several ambitious strategies for transforming Mars into a habitable world. Each method comes with its own challenges and uncertainties. Releasing greenhouse gases. 1. Concept: introduce greenhouse gases like CO2, methane, and water vapor to trap heat and warm the planet. 2. Challenges: Mars lacks significant CO2 reserves, and large-scale production would require massive industrial efforts. Giant space mirrors. 1. Concept: positioning large orbital mirrors to reflect sunlight onto Mars, increasing surface temperatures. 2. Challenges: constructing and maintaining kilometer-wide structures in space would be technologically and economically demanding. Nuclear detonations at the poles. 1. Concept: controlled nuclear explosions could vaporize frozen CO2 in polar caps, thickening the atmosphere. 2. Challenges: this method raises serious concerns regarding radioactive contamination and long-term planetary stability. Creating a magnetic shield. 1. Concept: placing an artificial magnetic shield at Mars' Lagrange point L1 to deflect solar wind and preserve the atmosphere. 2. Challenges: no existing technology can generate a stable, large-scale artificial magnetosphere. Introducing engineered microorganisms. 1. Concept: deploying genetically modified cyanobacteria and algae to produce oxygen and enrich the atmosphere. 2. Challenges: the harsh Martian environment could prevent microbial survival, requiring bioengineered resilience. Ethical and environmental considerations. Terraforming Mars presents profound ethical and environmental dilemmas that must be carefully evaluated. The right to alter a planet. 1. Some argue that Mars should be preserved in its natural state, particularly if microbial life exists beneath its surface. 2. Others believe that modifying Mars is part of humanity's destiny to expand and explore. Unintended ecological consequences. 1. Introducing Earth-based organisms could create unforeseen disruptions to any potential native Martian life. 2. Terraforming efforts could lead to unstable climatic conditions that make the planet even less habitable. The risk of incomplete terraforming. 1. The process could take centuries or millennia, and incomplete efforts might result in a hostile, unstable environment. 2. Failure to sustain a terraformed Mars could render the planet inhospitable for future generations. The future of terraforming Mars. While full-scale terraforming remains beyond our current technological capabilities, continuous research is bringing us closer to understanding what's possible. Rocket advancements in spaceflight. Cheaper and more efficient rockets may make large-scale planetary engineering feasible. DNA, biotechnological innovations. Future breakthroughs could enable engineered life forms to survive and transform Mars. High-voltage sine, mega-scale engineering, advanced fusion energy and air-driven automation could provide the resources needed for long-term planetary modification. Africa, international collaboration. The success of terraforming would require global cooperation between governments, private industries, and research institutions. Conclusion: terraforming Mars represents one of the most ambitious scientific and engineering challenges of the future. While the road ahead is long, the potential rewards, expanding human civilization, unlocking new scientific discoveries, and securing our species' survival, make the pursuit of a habitable Mars an endeavor worth exploring. Whether through atmospheric manipulation, genetic engineering, or artificial magnetospheres, the dream of transforming Mars remains one of the most compelling frontiers of space exploration. While we may not see a fully terraformed Mars in our lifetime, each scientific advancement brings us one step closer to making a second Earth a reality.